So we thought a little bit about Newton's laws of motion. Let's take one really nice example of an application of those laws. And this is the case of free fall and terminal velocity. Okay, so let's start off with free fall. If we've got an object which is falling downwards, let's suppose I've got an object with a mass m and it's falling downwards because it's been pulled down by its weight. Let's assume for the moment, let's completely forget about any drag or air resistance, anything like that. Let's just imagine the only force on it is its weight. You can create this if you take a great big tube and a vacuum tube with the air taken out, you drop something, then you've got free fall. So it's freely falling. Well, we know the equation for W. W is equal to m times g. Weight is equal to mass times gravitational field strength. We also know as well that Newton's second law tells us that force is equal to mass times acceleration. F equals ma. Well, in this situation, the only force is the weight. So in this situation, the weight is going to be equal to mass times acceleration. Now you look at those two equations and it's staring you in the face, isn't it? That G and A have to be the same thing. A equals G. So what does that mean? What that means is that any object which is in free fall with no air resistance will accelerate towards the ground at exactly the same rate. It will accelerate, in fact, near the Earth, it will accelerate at 10 meters per second squared because the gravitational field strength is 10 newtons per kilogram. That's telling us, therefore, that it doesn't matter whether you've got a large object or a small object, it doesn't matter what the mass is, they're all going to accelerate down at the same rate. Now the story goes that this was tested by Galileo when he dropped two balls, a heavy ball and a light ball, from the Leaning Tower of Pisa. We don't think probably that was done from the Leaning Tower of Pisa, although it's quite likely he did do some experiment like that. And what he found was that if we can ignore air resistance, heavy objects and light objects all accelerate downwards at the same rate, namely 10 meters per second squared, and therefore they'll hit the ground at the same time. That was tested, as you may know, on the moon when one of the astronauts dropped a hammer and a feather, and because there's no air resistance, the only force on them was their weight, and because they were in free fall, they accelerated towards the surface of the moon at the same rate and hit the ground at the same time. So in free fall, it doesn't matter whether you're heavy or light, doesn't matter what your mass is, you will get the same acceleration. And in fact, we sometimes call G, instead of calling it the gravitational field strength, we sometimes call it the acceleration due to gravity. It's telling us how much an object is going to accelerate near the surface of the Earth due to the Earth's gravitational pull. So that's free fall. Every object, no matter what its mass, will freely accelerate near the surface of the Earth at exactly the same rate. But life's not quite as simple as that, because in real life there are more forces than just weight, and that means that you don't just keep accelerating. Suppose we've got a skydiver. Okay, so this is going to be my intrepid skydiver who's just jumped out of an aeroplane. Okay. He's just left the airplane up here in the distance, and he's falling downwards. Now, what's going on there in terms of the forces on it? Well, to understand this, we sometimes draw what's called a force diagram, or also called a free body diagram. And to keep things simple, we simplify the object down to a little dot, and we draw arrows. Remember, vectors. Forces can be shown as vectors using arrows. We draw little vectors to show the forces. So here's our intrepid skydiver. He's just jumped out of the aeroplane. He's falling downwards. Why is he falling downwards? Well, obviously he's been pulled downwards by the force of gravity by his weight. So he's going to accelerate. If we drew a graph to show his velocity as a function of time, he comes out of the aeroplane, he's starting to get quicker and quicker and quicker because he's been pulled downwards by gravity. But in real life, as I say, we can't just think about weight, we also have to take into account drag or air resistance. That's a frictional force which acts effectively due to the fact that as you fall through the atmosphere, you're bombarding the air molecules and they're pushing back on your feet. It's Newton's third law of air. So as he gets quicker, he bangs against more molecules. So this is a drag force, and the drag force opposes his motion because it's a frictional force, and it's going to reduce the resultant force on our skydiver. Now you have to be very careful at this point. People start to say, oh, he's slowing down. Well, no, he's not. There's still more downwards force than upwards force. All that's happened is that the resultant force has started to get less. This force, the drag force, is starting to cancel out the weight. There's still a downwards force, he's still getting faster, but he's not going to be getting faster quite as much. Remember Newton's second law, force equals mass times acceleration, and what we said is that that F there is the resultant force. So if I've now got a drag force opposing my weight, I've still got a resultant force downwards, but it's not as much anymore. So if the resultant force is a bit less, then the acceleration will start to go down. And what that will look like on our velocity graph is that he'll be getting quicker, for sure, but he won't be getting quicker as quickly. He'll be accelerating less. But he's still getting quicker, right? So the drag force is still going to get bigger and bigger, and eventually, of course, the drag force will be equal and opposite to the weight. At this point, the forces balance each other perfectly. They cancel each other out. The resultant force is now going to be 0 because the drag cancels the weight perfectly. And if the resultant force is 0, that means the acceleration is 0. Acceleration of 0, what does that mean? It means constant velocity. So on our velocity time graph, what's going to happen is it's going to level out at a certain velocity which we call terminal velocity. Now this is a lovely example of Newton's second law. Notice that the forces haven't gone away, they're still there, but they're perfectly balanced, and therefore he's moving at a constant velocity. In fact, it's an example of Newton's first law as well, because we've got balanced forces and we've got motion in a straight line at a constant speed, falling downwards at a constant speed called terminal velocity. And that's quite a cool thing. If you look at videos of this on YouTube, when people reach terminal velocity, they're not strictly weightless because the weight's still there, but it's been perfectly balanced by the drag force. So they've got balanced forces on them and they can start doing all kinds of nice tricks, turning over, making it look as if they were weightless, even though in fact they've still got weight, but it's just been perfectly balanced by the drag. So, nice example of the application of Newton's first and second laws.